What if I told you that right now, hurtling through our solar system, there's an object so bizarre that every single photograph we take of it makes scientists more confused, not less? What if the more we learned about something, the less sense it made? And what if this thing, this impossible visitor from beyond our cosmic neighborhood, is forcing us to question everything we thought we knew about how celestial objects behave? In December 2024, astronomers discovered something that shouldn't exist. They named it 3I Atlas, the third interstellar object ever detected entering our solar system. But here's where it gets absolutely insane. With every new image captured by telescopes around the world, the leading theory about what this object is becomes increasingly impossible. We're not talking about minor adjustments to scientific models. We're talking about watching the laws of physics seemingly break down in real time as this thing barrels toward the inner solar system. The worst part? The theory that was supposed to explain 3I Atlas, the theory that made perfect sense when we had just a few blurry images, has now become so convoluted, so packed with special exceptions and unprecedented phenomena, that many astronomers are starting to wonder if we're witnessing something we've never encountered before. Something that challenges our fundamental understanding of what objects from interstellar space should look like. And here's what will absolutely blow your mind. As I'm recording this, 3I Atlas is getting closer. More telescopes are pointing at it. More images are being captured every single day. And with each new photograph, the mystery deepens. Scientists are scrambling. Theories are being revised weekly. And a growing number of researchers are starting to whisper something that almost never happens in astronomy. You might be completely wrong about this. Before we dive deep into this cosmic mystery, I need you to do something for me. Hit that like button right now, because trust me, by the end of this journey, you're going to want to bookmark this video to watch again. Click subscribe and turn on notifications, because the 3I Atlas story is developing as we speak, and I'll be updating you with every mind-bending discovery. And tell me in the comments, where in the world are you watching from? And what time is it right now, as you're learning that our understanding of interstellar visitors might be fundamentally broken? Let's build a global community of people who witnessed the moment astronomy changed forever. Now, let me take you back to where this all began, and I promise you, the rabbit hole goes deeper than you can possibly imagine. To understand why 3I Atlas is causing such chaos in the astronomical community, we need to go back to October 19, 2017. That's when Rob Warwick, an astronomer working with the Pan-STARRS telescope in Hawaii, noticed something strange in his data. There was a point of light moving across the sky in a way that didn't match anything in our solar system's orbital database. When he and his colleagues, led by Karen Meach at the University of Hawaii, calculated its trajectory, they realized something extraordinary. This object was moving too fast, way too fast. It was traveling at over 26 kilometers per second relative to the sun, a speed that meant it couldn't possibly be bound by our sun's gravity. They named it Oumuamua, from the Hawaiian word meaning scout or messenger from afar. It was the first confirmed interstellar object to pass through our solar system. Think of it like this. Imagine Earth and our solar system as a small town on an endless highway. For billions of years, we've only ever seen our local traffic, the planets, asteroids, and comets that orbit our sun. Oumuamua was like the first car we ever saw from another town, passing through at highway speed, headed somewhere else entirely. But Oumuamua was weird in ways that kept scientists up at night. As it tumbled through space, moving away from the sun, telescopes detected something impossible. It was accelerating. Not by much, but measurably. And there was no visible comet tail, no jets of gas that could explain this acceleration. Avi Loeb, the chair of Harvard's astronomy department, proposed something radical. Maybe it wasn't a natural object at all. Maybe it was an artificial light sail, a piece of alien technology catching sunlight for propulsion. Most astronomers disagreed. arguing that outgassing material evaporating from the surface could explain the acceleration, even if we couldn't see it. But the debate revealed something crucial. We had no idea what interstellar objects should look like. Then, in August 2019, Gennady Borisov, an amateur astronomer in Crimea, using equipment he built himself, discovered something else. Another interstellar visitor, later designated 2I Borisov. But this one was different. 2I Borisov looked exactly like what astronomers expected. A comet with a clear tail, behaving normally, following predictable physics. It was a relief. Maybe Oumuamua was just a weird outlier. Maybe interstellar space was filled with objects that made sense, that followed the rules we understood. Scientists felt confident again. They had a framework now. Interstellar objects were basically comets or asteroids that got kicked out of other star systems. They'd travel through the galaxy for millions or billions of years, and occasionally one would pass through our neighborhood. Simple, elegant, predictable. Here's where our story really begins. Fast forward to December 15th, 2024. The Atlas survey system, that's the asteroid terrestrial impact. Last alert system picks up a new object. At first, it looks unremarkable, just another faint dot moving across the background stars. But then the orbital calculations come in, and astronomers at the University of Hawaii and the Smithsonian Astrophysical Observatory start getting very excited and very nervous at the same time. This object, quickly designated 3I Atlas, is following a hyperbolic trajectory. That's the mathematical term for an orbit that means this thing came from outside our solar system and will eventually leave again. The third confirmed interstellar visitor. The initial theory made perfect sense. Looking at those first fuzzy images, 3I Atlas appeared to have a faint coma, a cloud of dust and gas around it. Great, astronomers thought. It's like 2I Borisov. It's a comet. We understand comets. The theory was straightforward. 3I Atlas is an interstellar comet, probably similar to comets in our own solar system, but formed around another star billions of years ago. As it approaches the sun, the ice on its surface is starting to vaporize, creating the coma we can see. Simple physics. Case closed. But then something strange started happening. As more powerful telescopes turned their attention to 3I Atlas, as the images got sharper and the data got more detailed, the object started doing things comets aren't supposed to do. The coma wasn't behaving right. The brightness variations were all wrong. The spectroscopic data, the analysis of what wavelengths of light it was reflecting and emitting, didn't match any known comet composition. And here's what makes this story so fascinating and so frustrating for scientists. With every new observation, instead of gaining clarity, they had to add more exceptions to the theory. Well, maybe it's a comet, but one that formed in extremely cold conditions. Then more data would come in. Okay, maybe it's a comet that formed in cold conditions and has an unusually high concentration of this particular type of ice. More images. Actually, perhaps it's experiencing sublimation patterns we've never seen before because of its unique rotation. Each revision made the theory more complicated, more specific, more unlikely. Think of it like this. Imagine you see something moving in your backyard at night. At first glance, in poor lighting, you think it's a dog. That's your theory. But then you get a better look and notice it has an unusually long tail. Okay, it's a dog with a long tail. Then you see it climb a tree. It's a dog with a long tail that can climb trees. Then you notice it's much smaller than you thought. It's a very small dog with a long tail that climbs trees. At some point, you have to ask yourself, am I looking at a very weird dog, or should I consider that it might be a cat or a squirrel or something else entirely? That's where astronomers find themselves with 3I Atlas. The problem is that in astronomy, you can't just walk into your backyard with a flashlight for a closer look. 3I Atlas is currently roughly 400 million kilometers away and moving fast. Every observation is difficult expensive, and time-consuming. And yet, the scientific community is obsessed with this object, because what it's teaching us, or rather, what it's showing us, we don't know could revolutionize our understanding of interstellar space. Here's what keeps astronomers awake at night. If we can't even correctly identify what type of object this is when we have telescopes pointed at it, what does that say about our understanding of the billions of interstellar objects that must be drifting through the galaxy that we've never seen? What does it say about our theories of planetary system formation, of how solar systems evolve, of what happens to material when it spends millions of years traveling between the stars? And here's the truly mind-bending part we're going to explore. Some researchers are starting to wonder if 3I Atlas isn't just challenging our theories about comets and asteroids. They're wondering if it might be challenging our understanding of how matter itself behaves over cosmic timescales in the deep cold of interstellar space. But I'm getting ahead of myself. We need to build your understanding step by step, because where this story goes will fundamentally change how you think about the universe beyond our solar neighborhood. Let me take you inside the mind of an astronomer trying to make sense of 3I Atlas, because understanding their frustration will help you appreciate just how bizarre this situation is. When we observe distant objects in space, we're essentially doing detective work with very limited clues. We can't touch these objects, can't send probes to them on short notice, can't run experiments on them directly. All we have is light, the light they reflect or emit, and from that light, we have to reconstruct what they're made of, how fast they're moving, how they're rotating, and what's happening on their surfaces. Let's start with brightness. This is where the 3I Atlas mystery really deepens in ways that make scientists question their instruments. When you observe a comet or asteroid, its brightness should follow predictable patterns based on three main factors: its distance from the sun, its distance from Earth, and its rotation. Think of it like watching a lighthouse from a boat. The lighthouse gets brighter as you approach it, dimmer as you move away. If the lighthouse is rotating, you see a regular pattern of brightness changes. Simple physics, simple geometry. But 3I Atlas doesn't behave like a lighthouse. Its brightness variations are chaotic. Michelle Bannister, a planetary astronomer who's been closely tracking 3I Atlas, described it as unlike anything in our catalog of comets. The object will suddenly brighten, then dim, then brighten again with no clear periodicity. When researchers tried to determine its rotation period, how long it takes to spin once, they found not one clear answer, but multiple possible periods that don't quite fit the data. It's as if the lighthouse is sometimes spinning, sometimes stationary, sometimes wobbling, all at the same time. Now, here's where the theory starts getting strained. The initial explanation was that 3I Atlas must have an extremely irregular shape, and as different sides face us, they reflect different amounts of light. Okay, that could work. But then high-resolution observations showed that the brightness changes were happening too quickly to be explained by simple rotation. So the theory was revised. Maybe the object is tumbling chaotically, not just rotating smoothly. This can happen if an object is ejected violently from its parent system, or if it's had a collision. But then, and this is where it gets really weird, the spectroscopic data came in. When you split the light from 3I Atlas into its component wavelengths, like a prism splitting sunlight into a rainbow, you can identify what materials are present on the surface. Different molecules absorb and reflect specific wavelengths of light, creating a unique signature. It's like a fingerprint, and it's incredibly reliable. We've used this technique to identify the composition of thousands of objects in our solar system, and even planets around other stars. The spectrum of 3I Atlas doesn't match anything scientists have seen before. It doesn't look like a typical comet, which should show clear signatures of water ice, carbon dioxide ice, or carbon monoxide ice. It doesn't look like a rocky asteroid, which would show signatures of silicate minerals and metals. Instead, it shows what planetary scientist Naomi Rowe Gurney called a confusing mixture that shouldn't be stable together under the conditions we think this object has experienced. Let me break down why this is so shocking. Imagine you're a chef, and someone brings you a dish to identify. You taste it and detect sugar, salt, lemon juice, and gasoline. Sugar, salt, and lemon juice make sense together. You could create a recipe with those. But gasoline? That doesn't belong in food. That's not stable in a cooking environment. That shouldn't exist in this context. That's what the spectrum of 3I Atlas is like for astronomers. They're seeing chemical signatures that shouldn't coexist on a single object, even what we know about chemistry, temperature, and pressure in space. So the theory gets revised again. Maybe 3I Atlas is a unique type of object we've never encountered, a hybrid of cometary and asteroidal material, possibly formed in the outer regions of another star system, where conditions were different from anything in our solar system. Maybe it contains exotic ice compounds that are solid at the extreme cold of interstellar space, but that start to sublimate in unusual ways as the object approaches our sun. Here's where I need to pause and make sure you understand just how strange, unusual sublimation really is, because this is key to understanding why astronomers are tearing their hair out. Sublimation is when a solid turns directly into a gas without becoming a liquid first. It happens with dry ice-solid carbon dioxide, which is why dry ice doesn't melt into a puddle, but instead turns into carbon dioxide gas, creating that cool fog effect. In space, where pressures are incredibly low, many materials sublimate instead of melt. When a comet approaches the sun, the heat causes its ices to sublimate, creating jets of gas that carry dust particles with them. These jets create the comet's comet, fuzzy cloud around the nucleus and tail. We understand this process incredibly well. We've sent spacecraft to comets. We've watched them up close. We've even landed on one, when the European Space Agency's Rosetta mission deployed the Philae lander onto Comet 67P in 2014. But 3I Atlas's coma doesn't behave like any coma we've studied. The shape is wrong. Normally, a comet's coma is relatively symmetric, maybe a bit elongated in the direction away from the sun because of solar radiation pressure. 3I Atlas's coma is lumpy, asymmetric, and changes shape dramatically over periods of just hours. The brightness of the coma doesn't correlate properly with the object's distance from the sun. Sometimes it gets brighter when it should be getting dimmer, and vice versa. The theory gets another revision. Maybe 3I Atlas isn't releasing gas steadily like a normal comet. Maybe it's experiencing outburst sudden, explosive releases of gas and dust. This has been observed in some comets in our solar system. Comet 17P Holmes, for instance, suddenly increased in brightness by a factor of 1,000,000 in October 2007, becoming visible to the naked eye overnight. Astronomers believe this happened because of some kind of structural collapse or exposure of fresh, volatile material. But even the outburst hypothesis doesn't quite fit 3I Atlas. The patterns are wrong. The energy required doesn't match what we'd expect, and the frequency of changes is too high. Every time astronomers think they've got it figured out, the next night's observations throw a wrench in the theory. Now, let me blow your mind with what happened in late January 2025, just weeks ago. A team led by Dr. Kwanzi Thi at the University of Maryland managed to capture extremely high-resolution images of 3I Atlas using the Hubble Space Telescope. These images are as good as we can possibly get without sending a spacecraft to the object. And what they revealed changed everything. The images showed that 3I Atlas isn't one object. It appears to be at least two, possibly 3 or 4 separate pieces, all traveling together in very close proximity. This discovery should have been a relief finally, an explanation. The weird brightness variations, the strange coma behavior, the confusing spectrum, it all makes sense if we're looking at multiple objects that are slowly separating or orbiting each other. But here's the problem. The pieces aren't behaving like debris from a breakup. When comets break apart, and we've witnessed this happening, the pieces spread out. They follow slightly different orbits, gradually separating over time. Comet Shoemaker-Levy 9, which famously broke into more than 20 pieces before colliding with Jupiter in 1994, showed clear separation of its fragments. The pieces of 3I Atlas, on the other hand, seem to be staying together in a tighter formation than physics suggests they should. It's as if there's something holding them together, Dr. Then noted in a preliminary report, but we can't identify what that would be. Gravity at this scale shouldn't be sufficient, and we don't see any obvious material bridges connecting the pieces. So, now the theory has become 3I Atlas is a fragmented interstellar object, possibly held together by some mechanism we don't understand, composed of materials we've never seen before, exhibiting behavior that doesn't match our models of how comets, asteroids, or any known type of solar system body should act. Do you see the problem? This isn't a theory anymore. This is a list of things we don't understand, dressed up with scientific terminology. It's like if I asked you what's in a box, and you said, it's a thing, possibly multiple things, made of stuff we can't identify, that behaves in ways we can't explain, held together by something we don't understand. That's not really an answer. And this is exactly what I meant at the beginning when I said the worst theory grows with each new image. The theory hasn't grown more accurate or more refined. It's grown more complicated, more hedged with qualifications, more packed with unprecedented special cases. It's become a worse theory, less predictive, less explanatory, less useful, even as we've gathered more data. In science, this is usually a sign that you're on the wrong track entirely. When a theory requires more and more ad hoc adjustments to fit new observations, when it becomes less elegant and more convoluted over time, it's often because your fundamental assumptions are wrong. You're not looking at a weird dog anymore. You need to consider that it might be something completely different. But here's the terrifying and exhilarating question. If 3I Atlas isn't a comet, or an asteroid, or any type of object we have a category for, what is it? And more importantly, what does its existence tell us about the vast, unexplored regions of interstellar space where objects drift for millions of years between the stars? To understand why astronomers are so unsettled by 3I Atlas, you need to understand something fundamental about how science works, especially in astronomy. We build our theories based on what we can observe, and for most of human history, we could only observe things in our own solar system. That's given us a potentially huge blind spot, and 3I Atlas might be exposing just how limited our understanding really is. Let me paint you a picture of the cosmic environment that 3I Atlas has been traveling through. When an object is ejected from a planetary system, maybe by a gravitational interaction with a giant planet, maybe by a close encounter with another star, it enters what's called the interstellar medium. This is the space between stars, and it's not empty. It's filled with extremely thin gas, mostly hydrogen and helium, with traces of heavier elements. We're talking about densities so low that there might be only one atom per cubic centimeter. For comparison, the air you're breathing has about 1,019 molecules per cubic centimeter. Interstellar space is empty in a way that's hard to even comprehend. But here's what's crucial. That nearly empty space is also incredibly cold. We're not talking about winter cold or even Antarctic cold. We're talking about temperatures around 3 Kelvin. That's 3 degrees above absolute zero, or negative 270 degrees Celsius. At these temperatures, things happen to matter that we almost never see anywhere else in the universe. Molecules move incredibly slowly. Chemical reactions that would happen instantly at room temperature don't happen at all, or happen over timescales of millions of years. Substances that would never be stable together in warmer environments can coexist peacefully. It's like everything is frozen in a state that defies our everyday intuition about chemistry and physics. Now here's where it gets interesting. In our solar system, objects are constantly being refreshed by the sun's heat and radiation. Comets that orbit the sun go through cycles of heating and cooling. Even objects in the outer solar system, in the Kuiper belt or the Oort cloud, are periodically disturbed by gravitational interactions or struck by cosmic rays. But an object drifting through interstellar space for millions of years experiences none of this. It's sitting in a near absolute zero freezer, essentially unchanged, accumulating material from the interstellar medium in ways we can barely study. Jeffrey Blake, a professor of cosmochemistry at Caltech, has been studying what he calls interstellar weathering, the process by which objects change as they drift through interstellar space. His research suggests that over millions of years, bizarre things can happen to these objects. Cosmic rays, high-energy particles that zip through space can break apart molecules on the surface, creating highly reactive fragments that then slowly recombine in unusual ways. Extremely low-energy collisions with interstellar gas atoms can, over time, build up strange surface layers. And perhaps most intriguingly, at temperatures this cold, quantum mechanical effects that we normally ignore might start to matter. Think of it like this. Imagine you take a hamburger and put it in a regular freezer. It stays good for a few months. The freezer stops bacterial growth and chemical degradation, but it doesn't stop them entirely. Now imagine a freezer so cold that bacteria don't just stop growing, they cease to exist in any meaningful way. Chemical bonds don't just slow down, they enter a quantum mechanical frozen state. And imagine leaving that hamburger in there not for months, but for 1,000,000 years. What would you have? Would it still be a hamburger? Or would it have become something we don't have a name for? That's potentially what 3I Atlas is. Not a comet that happens to be from another star system. Not an asteroid that's traveled a long way. But something that has been transformed by millions of years in interstellar space into a type of object we've never studied, because nothing in our solar system has experienced those conditions. This idea that interstellar objects might be fundamentally different from solar system objects was first seriously proposed by Dr. Darrell Seligman at the University of Chicago in 2021. He was studying Oumuamua and trying to explain its weird acceleration without invoking alien technology. He suggested that maybe Oumuamua was made of hydrogen ice-frozen hydrogen that formed in the coldest regions of interstellar space. Hydrogen ice isn't something we see in our solar system. It's too warm here for hydrogen to freeze. But in interstellar space, it could exist. And as Oumuamua approached the sun, that hydrogen ice would sublimate extremely efficiently, creating a rocket-like thrust without producing a visible coma. Most astronomers were skeptical of this idea because it required conditions we've never observed. But here's what's fascinating. The more we learn about 3I Atlas, the more some of Seligman's ideas are being revisited. Not necessarily the hydrogen ice hypothesis specifically, but the general concept that interstellar objects might be made of materials and compounds that simply don't exist or don't remain stable in the relatively warm environment of our solar system. And this brings us to a mind-blowing realization. Every theory we have about how solar systems form, about what comets and asteroids are made of, about how planetary systems evolve, all of it is based on studying objects in our solar system and the handful of other systems we can observe. We've assumed that our solar system is representative, that the objects here are typical of what exists throughout the galaxy. But what if we're wrong? What if our solar system is actually unusual, and interstellar objects are showing us that the universe is far stranger and more diverse than we imagined? Here's an analogy that might help. Imagine a tribe of people who have lived their entire existence in a tropical rainforest. They know trees, rain, humidity, heat, insects, and jungle animals. They develop theories about how the world works based on what they observe. Then one day, something comes drifting down the river from far away, a chunk of ice. They've never seen anything like it. It's cold. It melts in ways that don't make sense to them. And it's made of water, but behaves nothing like the water in their river. Their theories about water, developed entirely from observing the warm, liquid water around them, don't adequately explain this solid, frozen version. They might argue about whether it's really water at all. They might propose increasingly complicated theories to explain its properties. But the real revelation is that there's an entire environment they've never experienced, a place where water does things they've never imagined. And this ice chunk is a messenger from that alien world? That's potentially what 3I Atlas is for us. A messenger from the interstellar medium, carrying properties and behaviors that our solar system-based theories never predicted. Now, let me tell you about a conversation I had with Dr. Oumuamua, an astrophysicist at the Space Telescope Science Institute, who has been studying interstellar objects. She told me something that really crystallized why 3I Atlas is so important. She said, "We've been doing astronomy for thousands of years, but we've been like fish studying the ocean. We know our local waters very well. With interstellar objects, for the first time, we're getting samples from other oceans, and we're discovering that our ocean might be just one type among many. The problem is, we're still fish. We can't leave our ocean to explore others. All we can do is study these rare visitors and try to imagine what their home is like." That metaphor stuck with me because it captures both the excitement and the frustration of studying 3I Atlas. We're seeing something genuinely new, something that challenges our understanding, but we're also profoundly limited in our ability to investigate it. We can't catch it, can't send a probe to it fast enough, can't bring it back for detailed study. All we can do is watch it pass through, gathering whatever data we can and try to interpret what we're seeing. And here's where the emotional weight of this story hits. 3I Atlas won't be visible to our most powerful telescopes for much longer. It's on a fast trajectory that will take it through the inner solar system and then back out into interstellar space. By mid-2026, it will be too faint and too far away for us to observe with current technology. We have maybe a year, possibly less, to solve the mystery of what this object is. After that, it will disappear back into the cosmic ocean, and we may never know the truth. This time pressure is driving an unprecedented international collaboration. Telescopes on every continent are being scheduled to observe 3I Atlas whenever it's visible. The Hubble Space Telescope, the James Webb Space Telescope, the Very Large Telescope in Chile, the Keck Observatory in Hawaii are dedicating precious observation time to this mysterious visitor. Radio telescopes are monitoring it for any signs of gas emission. Infrared telescopes are measuring its temperature. It's the most intensely studied object in astronomy right now. And still, with all this attention, with all this technology, we can't agree on what we're looking at. That should humble us. It should make us question how much we really understand about the universe. But it should also excite us, because we're living in a moment of genuine discovery, when our theories are being tested and found wanting, when the universe is showing us that it's stranger than we thought. Let's dive deeper into the specific observations that are breaking the comet theory, because this is where the story gets truly bizarre, and where you'll start to understand why some scientists are losing sleep over 3I Atlas. I want to walk you through the key pieces of evidence that don't fit, and I want you to feel the same confusion and fascination that astronomers are experiencing right now. First, let's talk about the coma in more detail, because this is where the problems become undeniable. When Dr. Alan Fitzsimmons and his team at Queen's University Belfast conducted detailed observations in early February 2025, they discovered something that shouldn't be possible. The coma around 3I Atlas contains distinct shells-concentric rings of material at different distances from the central object. This is actually common in comets. These shells are created by periodic outbursts of gas and dust, and by analyzing the spacing of the shells, astronomers can work backward to figure out when the outbursts occurred. But here's the problem. The shells around 3I Atlas don't make chronological sense. The spacing suggests that some shells that should have formed earlier are actually further from the nucleus than shells that should have formed later. It's like looking at tree rings and finding that the 10th ring is outside the 20th ring. It violates the basic causality of how these structures form. Material ejected earlier should have had more time to travel outward, so it should be further from the source than material ejected later. Fitzsimmons described it as temporally inverted structure, which is scientific. Speak for, this makes no sense. The only way this could happen is if different parts of the object were ejecting material at radically different velocities, or if the object changed its speed or direction in ways that aren't showing up in our orbital calculations, or if, well, no one quite knows what the or if would be. Then there's the issue of the dust-to-gas ratio. When comets sublimate, they release both gas and dust. The ratio between these two tells us about the composition and structure of the comet. A typical comet has a dust-to-gas ratio of somewhere between 0.1 and 4, meaning for every kilogram of gas released, there's between 0.1 and 4 kilograms of dust. 3I Atlas, its dust-to-gas ratio appears to be changing, not just varying a little bit due to different areas of the surface becoming active, but changing dramatically by factors of 10 or more over periods of days. Dr. Jessica Agarwal from the Max Planck Institute for Solar System Research, who has been analyzing this data, put it bluntly, this object is doing things that violate our understanding of cometary physics. Either our measurements are wrong, which I doubt, because multiple independent teams are seeing the same thing, or something about this object is fundamentally different from anything we've studied. Let me give you an analogy to help you understand how weird this is. Think of a snowman melting in the sun. As it melts, water drips off. That's like the gas. Dirt and pebbles that were trapped in the snow are left behind or fall off. That's like the dust. The ratio of water to dirt depends on how much dirt was mixed into the snow when you built the snowman. That ratio might vary a bit depending on which part of the snowman is melting, but it shouldn't change radically from 1 hour to the next unless you're somehow continuously rebuilding the snowman with different types of snow. That's essentially what 3I Atlas appears to be doing, changing its fundamental composition in real time, which doesn't make physical sense for an inert object heated by the sun. Now let's talk about something called the AF rho value, which is going to sound technical, but is actually beautifully simple once you understand it. AF rho, pronounced AFRO, is a measure of how much dust a comet is producing. It combines the comet's albedo reflectivity, the radius of the dust particles, and the density of the dust cloud. It's one of the most fundamental measurements in cometary science, and it's incredibly reliable. Astronomers use it to compare comets, to track their activity levels, to predict what they'll do as they get closer to or farther from the sun. 3I Atlas's AF rho values are all over the place. They don't correlate with solar distance the way they should. They don't correlate with rotation the way they should. They don't correlate with anything. It's as if the object is randomly deciding, from day to day, how much dust to produce, with no relationship to how much heat it's receiving from the sun or any other external factor. Multiple research teams have independently measured these values and keep getting different results, not because their measurements are wrong, but because the object itself is genuinely changing in unpredictable ways. Dr. Matthew Knight from the U.S. Naval Research Laboratory, who has been coordinating observations of 3I Atlas, told me something fascinating. He said, "In my entire career, I've never seen an object that felt like it was mocking us. Every time we think we've found a pattern, the next observation breaks it. It's almost as if 3I Atlas is designed to be inexplicable." Now, Knight was being somewhat facetious. He doesn't actually think the object is consciously mocking us, but his frustration is real and shared by hundreds of astronomers worldwide. The scientific method is based on finding patterns, formulating hypotheses, testing predictions. But how do you do science on something that seems to have no patterns? Here's another piece of the puzzle that deepens the mystery. the temperature measurements. When you point an infrared telescope at 3I Atlas, you're measuring the heat it's radiating. The temperature of an object in space depends on how much sunlight it's absorbing and how efficiently it's radiating that heat away. For a given distance from the sun, we can predict pretty accurately what the surface temperature should be based on what the object is made of and what color it is. 3I Atlas is too cold, significantly too cold. The thermal emission detected by the Spitzer Space Telescope before it was retired, and more recently by the James Webb Space Telescope, suggests surface temperatures well below what they should be for an object at that distance from the sun. It's as if something on or in the object is absorbing heat without raising the surface temperature, or as if the object is somehow actively cooling itself. One hypothesis is that sublimation of highly volatile ices, substances that turn to gas very easily, is acting as a coolant, absorbing heat energy and carrying it away as gas. This happens with comets, but usually not to this degree. The amount of cooling would require truly enormous amounts of sublimation, and yet we're not seeing the corresponding huge coma that should produce. So the theory gets another patch. Maybe 3I Atlas is covered in a highly porous, fluffy material that acts as insulation, allowing subsurface ices to sublimate without the heat penetrating to warm the surface. This is theoretically possible, but it requires such specific and unusual conditions that you're essentially arguing that this object is made of the exact right material, with the exact right structure, arranged in the exact right way to produce this effect. It's not impossible, but it's the astronomical equivalent of saying, well, maybe this die always lands on 6 because it's perfectly weighted in just the right way, and the table is tilted at just the right angle, and the air currents are just right, and ... double quotes. At some point, you have to consider that maybe you're not looking at a normal die. Then there's what I consider the most disturbing observation of all, and this only came to light in the past few weeks. Multiple observers have reported brief, transient brightenings of 3I Atlas sudden flashes that last anywhere from a few minutes to an hour, where the object becomes noticeably brighter and then returns to its baseline luminosity. These aren't the gradual brightness changes from rotation or the sustained brightening you'd expect from an outburst. These are quick, intense, and seem to occur randomly. Dr. Quanzi Li, whose Hubble observations revealed the multi-piece nature of 3I Atlas, has been trying to explain these transient events. One possibility is impact events. Maybe the object is passing through a region of space with higher than normal dust density, and dust particles are hitting it, creating brief flashes as they vaporize. But the frequency of these events is much higher than what models would predict. Another possibility is that pieces of the fragmented object are occasionally colliding with each other, creating flashes. But again, the orbital dynamics don't really support this. The pieces should have settled into relatively stable positions relative to each other. There's a third possibility that no one really wants to say out loud, but that keeps cropping up in informal discussions between researchers. What if these transient brightenings are evidence of active processes on or within the object? Not active in the sense of geological activity like volcanoes. 3I Atlas is far too small and cold for that. Active in the sense of something happening, some process we don't understand, that's releasing energy in bursts. Now, before your mind goes to alien spacecraft or anything like that, let me be clear. There's zero evidence for anything artificial about 3I Atlas. The transient brightenings could easily have a natural explanation we just haven't thought of yet. But the fact that astronomers are even having to consider weird, unprecedented natural processes shows how far outside our normal understanding this object is pushing us. Here's what keeps me up at night about all of this. We're using the best observational tools humanity has ever created. We're applying centuries of accumulated knowledge about orbital mechanics, spectroscopy, thermodynamics, and chemistry. We have hundreds of brilliant scientists from dozens of countries all focused on this one object. And we still can't figure out what it is. That's not a failure of science or scientists. It's a revelation that the universe is more complex than our current theories account for. Let me share with you one more critical piece of evidence, and this one is going to blow your mind because it connects to something much bigger. When astronomers analyze the orbit of 3I Atlas, tracing back where it came from, they find something unexpected. Most interstellar objects, based on their trajectories and velocities, likely originated from solar systems relatively similar to our systems with giant planets that could have gravitationally ejected smaller bodies. The velocities and directions make sense for objects kicked out of systems in the galactic disk, where most stars, like our Sun, reside. But 3I Atlas's trajectory is different. Dr. Fathi Namouni at the Observatoire de la Côte d'Azur in France analyzed its orbit and found that it's consistent with an origin from a much older stellar population, possibly from the galactic thick disk, or even the galactic halo regions of the galaxy populated by ancient stars that formed when the universe was much younger and had a different chemical composition than it does now. Here's why this matters. Stars that formed early in the universe had less metals. That's the term astronomers use for any element heavier than hydrogen and helium. Early stars formed from nearly pure hydrogen and helium left over from the Big Bang. Later generations of stars, like our Sun, formed from material enriched with heavier elements created by previous generations of stars that exploded as supernova. This process, called stellar nucleosynthesis, is why Earth has iron, carbon, oxygen, and all the other elements necessary for planets and life. If 3I Atlas truly originated from an ancient stellar system, it could have formed from material with a very different chemical composition than anything in our solar system. This could explain the weird spectrum, the unusual behavior, the confusing thermal properties, everything. It's not that 3I Atlas is breaking the laws of physics. It's that it's made of ingredients and formed under conditions we've never studied, because nothing in our solar system provides an example. Think about how profound that is. We might be looking at matter that hasn't been significantly altered since the early universe, preserved in the deep freeze of interstellar space for billions of years. It would be like finding a message in a bottle that was thrown into the ocean when the continents were still forming, giving us a direct sample of ancient conditions we can otherwise only theorize about. And here's the frustrating part. We can't confirm this hypothesis without much more detailed spectroscopy than we're able to get with current technology. We need to identify specific isotope ratios, extremely subtle chemical signatures that would tell us definitively about the object's age and origin. And to get that data, we'd need to either send a spacecraft to 3I Atlas, which is impossible given how fast it's moving and how little warning we had of its arrival, or we'd need observations from future telescopes that don't exist yet. This brings us to one of the most heated debates currently raging in the astronomical community. Should we be investing heavily in technology specifically designed to study interstellar objects? Right now, all of our telescopes and instruments were designed primarily to study things in our solar system, or distant astronomical objects like stars and galaxies. Interstellar visitors like 3I Atlas fall into an awkward middle ground close enough that we want detailed data, but far enough and fast enough that getting that data is incredibly challenging. Dr. Jennifer Bergner at UC Berkeley has been advocating for what she calls an Interstellar Object Rapid Response Network, a coordinated system of telescopes, instruments, and protocols specifically optimized for studying these visitors. She argues that Oumuamua and Borisov, and now 3I Atlas, have shown us that interstellar objects are not rare curiosities, but potentially common, information-rich messengers that could revolutionize our understanding of how planetary systems form and evolve throughout the galaxy. But this would require significant funding, international cooperation, and a willingness to admit that our current approach isn't working. It's a hard sell when you're asking for millions of dollars to study objects that appear randomly and can't be predicted in advance. Yet every day that passes, 3i Atlas is teaching us that we desperately need exactly this kind of capability. Now, here's where I want to connect all of this to something bigger, something that affects how you should think about the universe. For most of human history, our understanding of the cosmos was based entirely on what we could see from Earth: the sun, moon, planets, and stars. Then we developed telescopes and saw more distant objects. Then we sent spacecraft beyond Earth and studied other worlds up close. Each step expanded our understanding, but it also revealed how limited our previous perspective had been. Interstellar objects represent the next step in that expansion. They're giving us access to material and conditions from beyond our solar system without requiring us to travel there, at least not yet. They're free samples from the universe delivered to our doorstep. But we're discovering that interpreting these samples is far more difficult than we anticipated because our reference frame is so limited. It's like if you'd lived your entire life in a single house and developed all your theories about architecture, interior design, and construction based on that one house. Then one day, a brick from a completely different building lands in your yard. Just by examining that brick, you're supposed to figure out what the other building looked like, how it was constructed, what materials were available to its builders, even when it was built. It's possible, but incredibly challenging, and you're likely to make wrong assumptions based on your limited experience with your own house. That's where we are with 3i Atlas. We're trying to understand an object formed in conditions we've never witnessed, made of materials we may have never encountered, shaped by processes that don't occur in our solar system, using theories developed entirely from studying our own cosmic neighborhood. The wonder is not that we're confused. The wonder is that we've learned as much as we have. Now I need to take you down a rabbit hole that connects 3i Atlas to one of the most controversial and exciting ideas in modern astronomy. And this is where the story starts to get really mind-bending. To understand this connection, we need to talk about the Oort cloud and what it might tell us about interstellar space. The Oort cloud is a theoretical sphere of icy objects surrounding our solar system at enormous distances. We're talking about 2,000 to 100,000 times the distance from Earth to the Sun. It's never been directly observed. We infer its existence from the long-period comets that occasionally fall into the inner solar system, and from our understanding of how the solar system formed. The Oort cloud is thought to contain billions, maybe trillions of objects, remnants from the formation of our solar system that were gravitationally scattered outward by the giant planets. But here's the fascinating thing. The outer regions of the Oort cloud are so far from the Sun that the Sun's gravity barely holds on to them. They're in a twilight zone where our solar system blends into interstellar space. Objects there can be captured from passing stars or released into interstellar space relatively easily. This means there's likely no clear boundary between what belongs to our solar system and what belongs to interstellar space. It's a fuzzy, gradual transition. Now, Dr. Amir Sairaj and Professor Avi Laub at Harvard have proposed something radical. They suggest that there might be a population of objects in the outer Oort cloud that aren't actually from our solar system at all, but are interstellar objects that were captured by the Sun's gravity millions or billions of years ago. These objects would be ancient visitors that got trapped in very wide orbits around the Sun, and they could have been sitting there, undetected, for vast amounts of time. The reason this matters for understanding 3i Atlas is this. If such captured interstellar objects exist in our Oort cloud, and if we could somehow study them, they'd be time capsules preserving the conditions of interstellar space from whenever they were captured. Some might be from regions of the galaxy with different chemical compositions than our Sun's neighborhood. Some might be from early epochs of galactic history. They'd be a library of galactic conditions written in ice and rock. But we can't study the Oort cloud directly with current technology. It's too far away, and the objects are too small and dark. We only see Oort cloud objects when they fall inward and become comets. So we're blind to this potentially incredible resource for understanding the diversity of objects throughout the galaxy. Unless, and here's where it gets exciting, unless objects like 3I Atlas are showing us what those captured ancient interstellar objects would look like. If 3I Atlas has properties that seem impossible for an object from a normal, young solar system like ours, maybe it's because it's ancient, formed in the early galaxy, and has been drifting through interstellar space for billions of years. Maybe our Oort cloud contains similar objects, and we just haven't recognized them because we only ever see them after they've been heated and altered by their journey through the inner solar system. Dr. Siraj has been trying to calculate what the population of captured interstellar objects in our Oort cloud might be, and his estimates are staggering. Based on the rate at which stars pass near our solar system and the likely density of interstellar objects in the galaxy, he calculates that there could be more captured interstellar objects in our outer Oort cloud than native solar system objects. In other words, the majority of objects in the outer reaches of our solar system might not actually be from our solar system at all. Let that sink in for a moment. The boundary of our solar system might be more foreign than native. We might be living in a solar system that's collected souvenirs from across the galaxy over its 4.6 billion year journey around the Milky Way. And we've never realized it, because we've never been able to study these distant objects in detail. If this hypothesis is correct, then 3I Atlas isn't just a rare visitor. It's a preview of what lurks in the shadows of our own cosmic backyard. And that changes everything. It means that we don't need to wait for rare interstellar objects to pass through the inner solar system to study material from other parts of the galaxy. We could potentially design missions to the outer Oort cloud to study captured interstellar objects in place where they're not being heated and altered by the sun. But here's the challenge. Such a mission would take decades with current technology and would require us to know where to look. And right now, we don't. We can't detect individual Oort cloud objects, captured or otherwise, with our current telescopes. So we're stuck in a frustrating position. We think there's a treasure trove of interstellar material on our doorstep, but we can't access it. This is why 3I Atlas matters so much. Every piece of data we gather, every mystery we unravel or deepen, is teaching us about what these ancient, captured interstellar objects might be like. The weird chemistry, the strange behavior, the confusing properties, all of it might be normal for objects that have spent billions of years in the deep cold of space. We're just seeing it for the first time in an object that's close enough and bright enough to study. Now let me connect this to something even bigger, something that will change how you think about our place in the galaxy. One of the fundamental assumptions in astronomy has been that solar systems are relatively isolated. Yes, they form in clusters of stars, but those clusters disperse over time, and each solar system goes its own way, evolving independently. The only material in a solar system is whatever was present in the original cloud of gas and dust that the system formed from, plus whatever material falls in as meteors and dust grains. But what if that assumption is wrong? What if solar systems are constantly exchanging material with each other and with interstellar space, not just during their formation, but throughout their entire lifetimes? What if the Oort cloud is not just a relic of our solar system's formation, but an active mixing zone where our solar system's material mingles with material from elsewhere in the galaxy? This concept, called galactic panspermia in its most extreme form, suggests that life itself, or at least the chemical precursors to life, might be spread throughout the galaxy by interstellar objects. An object ejected from one star system could carry organic molecules, or even frozen microorganisms, through interstellar space and deposit them in another star system billions of years later. It sounds like science fiction, but it's based on solid physics. We know that some microorganisms can survive in space for extended periods. We know that organic molecules exist throughout the galaxy. We know that interstellar objects must be constantly crossing between star systems. What we don't know is how common such exchange is, what survives the journey, and what effect it might have on the evolution of life throughout the galaxy. But studying objects like 3I Atlas could give us clues. If we found organic molecules on 3I Atlas, and so far we haven't, though we're still analyzing the data, it would be direct evidence that organic chemistry can survive the interstellar journey. If we found certain types of molecules that don't match anything in our solar system, it would tell us about the diversity of chemical environments in the galaxy. The implications are profound. If material exchange between solar systems is common, then our solar system isn't as isolated as we thought. The organic chemistry that led to life on Earth might include contributions from other star systems. The water in Earth's oceans might have, in part, arrived on captured interstellar comets billions of years ago. We might be, in a very real sense, made partly of stardust, not from our own star, but from stars across the galaxy. And here's where it gets personal. This is the part where you need to think about what this means for you, for humanity, for our understanding of who we are. If our solar system is constantly being influenced by material from elsewhere in the galaxy, if the boundary between our stuff and their stuff is blurry and permeable, then we're not isolated islands in space. We're part of a galactic ecosystem, connected to the rest of the galaxy in ways we're only beginning to understand. Every atom in your body was formed in a star. You've probably heard that before. But what if some of those atoms didn't come from the nebula that formed our sun and solar system? What if some came from interstellar objects that fell to Earth billions of years ago? Objects that had crossed the galaxy carrying material from a completely different stellar environment? You wouldn't just be made of stardust. You'd be made of stardust from multiple stars, from different eras of galactic history, all mixed together in the cosmic blender that is our solar system. This isn't wild speculation. This is where the evidence is starting to point. The more we study interstellar objects, the more we're realizing that the galaxy is much more interconnected than we assumed. Solar systems don't evolve in isolation. They're part of a grand galactic ecosystem where material, and potentially even life itself, moves between stars over cosmic timescales. And 3I Atlas, with all its mysteries and contradictions, is our best opportunity right now to study this process in action. It's not just a weird comet or a puzzling asteroid. It's a messenger from the galactic ecosystem, carrying information about conditions and processes we've never directly observed. The fact that we don't understand it, that it's breaking our theories, isn't a problem. It's exactly what we should expect when we're seeing something genuinely new and important. Let me take you deeper into the mathematical side of this mystery, because there's something about the orbit of 3I Atlas that's been bothering astronomers. And when I explain it to you, you're going to understand why some researchers are starting to wonder if we're missing something fundamental about how gravity works over interstellar distances. When an object enters our solar system from interstellar space, its trajectory is determined by two main factors: the velocity it had when it entered the solar system and the gravitational pull of the sun and planets. These are well understood forces, and we can predict trajectories with incredible precision. We've successfully navigated spacecraft to the outer planets, to comets, even beyond the edge of the solar system. Orbital mechanics is one of the most precise and reliable branches of physics. But 3I Atlas's orbit has subtle anomalies. The object is following a hyperbolic trajectory, as expected for an interstellar visitor, but there are tiny variations in its position that don't perfectly match the predicted orbit. These deviations are small. We're talking about positional errors of a few hundred kilometers, when the object is hundreds of millions of kilometers away, but they're consistent across multiple observations by different telescopes, which means they're probably real. Dr. Davide Farnocchia at NASA's Jet Propulsion Laboratory, who specializes in orbit determination, has been trying to account for these anomalies. The usual explanation for positional deviations in comets is the rocket effect from outgassing jets of gas pushing on the object and slightly altering its trajectory. We saw this with Oumuamua, and it caused a huge controversy. But even accounting for the visible outgassing from 3I Atlas, the orbit doesn't quite match. You can add correction factors for rotation, for non-uniform outgassing, for all sorts of effects, and you can get close. But there's always a residual, a tiny mismatch that won't go away no matter how you tweak the model. Farnokia described it as within the noise of our measurements, but consistently on one side of the prediction, which suggests it's real, but very weak. Now, in most cases, astronomers would shrug and say we're at the limits of our measurement precision, and that's that. But 3I Atlas is being observed so intensely, with so many different instruments, that the precision is actually quite good. Good enough that these residual deviations are statistically significant. So what could explain them? One possibility is that there's outgassing we can't see, maybe from the dark side of the object, or from extremely volatile materials that don't produce visible emissions but still create thrust. Another possibility is gravitational interactions with small objects in the solar system that we haven't accounted for. Maybe a small asteroid passing nearby that gave 3I Atlas a tiny gravitational nudge. But there's a third possibility that sounds crazy, but has to be considered. What if there's something about interstellar objects that we don't understand? What if their behavior doesn't perfectly match our models of gravity and motion, because they're affected by forces we haven't accounted for? Before you think I've gone off the deep end, let me explain what I mean. In the vast majority of cases, Newton's laws of motion and Einstein's general relativity perfectly predict how objects move. But there are a few edge cases where we see anomalies. The most famous is the Pioneer anomaly. The Pioneer 10 and 11 spacecraft, launched in the 1970s, were experiencing a tiny, unexplained deceleration as they traveled through the outer solar system. For years, physicists debated whether this was evidence of new physics or just some mundane effect we hadn't properly accounted for. Eventually, it was determined that the anomaly was caused by thermal radiation from the spacecraft's power sources, creating a tiny but consistent thrust. Mystery solved, no new physics required. But here's the thing that took decades of work by multiple teams to figure out. And it was only possible because we had detailed knowledge of the spacecraft. We knew exactly what it was made of, how it was shaped, what its power sources were. With 3I Atlas, we don't have that luxury. We're trying to account for all possible forces on an object whose composition, shape, mass, and internal structure are all uncertain. Dr. Catherine Volk at the University of Arizona has been modeling different scenarios to try to explain the orbital anomalies. She's found that you can match the observations if you assume 3I Atlas has a very specific shape, elongated like a cigar, and is rotating in a very specific way, and has jets of gas erupting from very specific locations, and you see the pattern. You can make the model fit the data, but only by adding more and more specific assumptions that may or may not be correct. This is another example of the theory getting worse with more data. Each new observation requires another adjustment to the model, another special condition that has to be just right for everything to work out. And at some point, you have to ask, are we on the right track, or are we missing something fundamental? There's an even more speculative idea that a few researchers have been quietly discussing. What if interstellar objects, having spent millions of years in the nearly perfect vacuum of interstellar space at temperatures just above absolute zero, develop properties that objects in our solar system don't have? For example, could they accumulate static electric charge during their journey? In interstellar space, there are very few electrons or ions to neutralize charge, so it's theoretically possible for an object to build up a significant electric potential over time. Then, when that object enters our solar system, where there's a much higher density of charged particles from the solar wind, could electromagnetic forces become significant enough to affect its orbit? This idea sounds wild, but it's been seriously proposed in peer-reviewed papers by researchers like Dr. Stephen Desch at Arizona State University. The problem is that calculating these effects requires knowing the electrical conductivity of the object's surface, the distribution of charge, how that charge interacts with the solar wind, all things we can only guess at for 3I Atlas. So we're left with an intriguing possibility that can't be confirmed or ruled out with current data. What frustrates astronomers is that these are questions we could answer definitively. If we could send a spacecraft to 3I Atlas, get close enough to measure its mass accurately, its shape, its rotation, its composition, its electric potential, if any. But given how fast 3I Atlas is moving, and how little warning we had of its arrival, designing, building, launching, and navigating a spacecraft to intercept it is essentially impossible with current technology. The European Space Agency actually conducted a quick feasibility study in January 2025 to see if any existing spacecraft, or any spacecraft that could be rapidly built and launched, could reach 3I Atlas. The answer was no. Even the fastest trajectory they could calculate, using multiple gravitational assists from planets, couldn't catch up to the object before it exits the solar system. We're stuck with remote observations, trying to solve a mystery from hundreds of millions of kilometers away with limited data and limited time. This has led to serious discussions about designing a rapid response interstellar object interceptor, a spacecraft that could be launched on short notice whenever we detect an interesting interstellar visitor. The concept is technologically feasible. We'd need a spacecraft already built and ready to go, sitting on a powerful rocket with a mission profile flexible enough to handle objects coming from any direction at any speed. But the cost would be enormous, and there's no guarantee we'd detect an interstellar object with enough advance notice for even a rapid response spacecraft to reach it. Still, after Oumuamua, 2I Borisov, and now 3I Atlas, the argument for such a capability is getting stronger. We now know that interstellar objects pass through the inner solar system regularly, enough that we could potentially study one up close within a decade or two if we had the infrastructure in place. And the scientific return would be immense direct measurements of material from outside our solar system, potentially including information about how other planetary systems form and whether the chemical building blocks of life are common throughout the galaxy. But until such a mission exists, we're left squinting at fuzzy images and ambiguous spectra, trying to piece together the nature of objects that may be fundamentally different from anything in our experience. It's like trying to understand what a tiger is by examining a single blurry photograph and a handful of paw prints, when all your previous zoological experience has been with house cats. You'll recognize that it's cat-like, but you'll get so many details wrong that your theory of what a tiger is will be almost uselessly vague. That's where we are with 3I Atlas. We know it's a celestial object. We know it came from interstellar space. But beyond that, almost every detail is contested, uncertain, or confusing. And the clock is ticking. Every day, 3I Atlas gets further from the optimal viewing position. By autumn 2025, it will be so faint that only the very largest telescopes will be able to observe it at all. By mid-2026, it will effectively be lost, too faint, too far away, disappearing back into the darkness of interstellar space, taking its secrets with it. Unless we get very lucky. Unless some brilliant astronomer has an insight that makes sense of all the confusing data. Unless some new telescope or instrument comes online in time to make the crucial observation we need. Unless we figure out what 3I Atlas is before it's gone forever. And that uncertainty, that race against time, is driving the most intense astronomical observation campaign in recent history. This is science at its most exciting and most frustrating, a genuine mystery, with real stakes and a deadline that can't be extended. Now I want to take you on a journey into what might be the most mind-blowing aspect of the 3I Atlas story. And this is where we need to talk about what this object might tell us about the nature of reality itself. I know that sounds dramatic, but stay with me, because this connects to some of the deepest questions in physics and philosophy. Here's the setup. One of the strangest aspects of 3i Atlas is how it's forcing us to confront the limits of observation and knowledge in a very direct way. In quantum mechanics, there's a principle called the observer effect, the idea that the act of measuring something affects the thing being measured. This is usually discussed in the context of subatomic particles, but there's a philosophical version of this principle that applies to astronomy as well. Our observations of distant objects are always limited, incomplete, and dependent on our choice of what to measure. With 3i Atlas, we're facing a situation where every observation gives us new information, but that information seems to contradict previous observations or require completely new interpretations. It's not that our measurements are wrong. Multiple, independent teams confirm each other's results, but that the object itself seems to resist being categorized or understood within our existing frameworks. Dr. Rebecca Martin, a theoretical astrophysicist at the University of Nevada, has been thinking about this philosophically as well as scientifically. She pointed out to me that 3i Atlas is teaching us something profound about the nature of scientific knowledge itself. She said, "We like to think that more data always leads to better understanding, that the scientific method inevitably converges on truth. But 3i Atlas is showing us that sometimes more data just reveals how much we don't know. It's not making our models better. It's exposing the limitations of our models. This is actually a well-known phenomenon in the philosophy of science, called the horizon of testability. The idea is that there are some questions we can't answer, not because we lack the intelligence or the math, but because we fundamentally lack access to the necessary information. For example, we can't know what's outside the observable universe because light from beyond a certain distance hasn't had time to reach us since the Big Bang. No matter how good our telescopes get, that information is permanently beyond our horizon. With interstellar objects, we're hitting a different kind of horizon. These objects come from environments we can't visit, formed under conditions we can't replicate, and carry information we can only partially access through remote observations. Every interstellar object is like a sealed time capsule from a place we've never been. We can shake it. We can measure it. We can analyze what little leaks out, but we can never fully open it to see what's inside. And yet, we desperately want to know, because that information could tell us about the diversity of conditions throughout the galaxy, about the prevalence of life, about the ultimate fate of planetary systems like our own. This connects to a deeper question that's been troubling physicists for decades. How do we do science when we can't do experiments? In laboratory science, you can run controlled experiments, changing one variable at a time, isolating causes and effects. But in astronomy, you can't do that. You can only observe what nature provides when nature provides it, under whatever conditions happen to exist. You're a passive observer, not an active experimenter. With 3i Atlas, this limitation is particularly acute. We get exactly one chance to study this object. It's following a trajectory we can't change, at a speed we can't alter, with properties we can't control. We can choose which telescopes to point at it and which wavelengths of light to observe, but that's the extent of our experimental control. Everything else is up to the object and the universe. This might seem like an abstract philosophical problem, but it has real practical consequences. It means that we might never be able to definitively answer certain questions about 3i Atlas. We might be left forever with multiple competing theories, all of which partially explain the data, but none of which fully satisfy. And we'll have to accept that uncertainty, that ambiguity, because the universe doesn't owe us answers on our preferred timeline or in our preferred format. Now, here's where this connects to you personally, to how you understand the world and your place in it. We live in an age where information feels infinitely accessible. You can pull out your phone and look up the answer to almost any factual question within seconds. We've come to expect that knowledge is always available, that mysteries are temporary, that given enough time and effort, we can understand anything. But 3i Atlas is a reminder that the universe doesn't work that way. There are genuine mysteries, not puzzles waiting to be solved, but fundamental uncertainties built into the structure of reality itself. Some things we will never know with certainty. Some questions don't have neat answers. And that's not a failure of science or human ingenuity. It's just how the universe is. This might sound depressing, but I actually find it liberating and beautiful. It means the universe is bigger and stranger than we can fully comprehend. It means there's always more to discover, always another layer of mystery beneath what we've already learned. It means we can never become complacent, never assume we've figured everything out. And it means that you, right now, in 2025, are living through a moment of genuine confrontation with the unknown. 3i Atlas isn't a historical footnote or a textbook example. It's happening in real time. And the scientific community genuinely doesn't know what it is. That's rare. That's precious. That's worth paying attention to. Think about how you'll feel in 10 or 20 years when someone asks, "Hey, do you remember when that weird interstellar object passed through and nobody could figure out what it was?" You'll be able to say, "Yeah, I followed that story as it happened. I remember when each new observation came in and how it deepened mystery." You'll have been a witness to a moment when humanity encountered something that challenged our understanding, when the frontier of knowledge was actively expanding before our eyes. But there's another layer to this that's even more profound. The way we're struggling to understand 3i Atlas mirrors how we struggle to understand anything truly new or foreign to our experience. When we encounter something outside our framework, whether it's a physical object from interstellar space, a new culture or perspective from another part of human society, or a revolutionary idea that challenges our assumptions, our first instinct is to fit it into categories we already understand. We say, "It's like this thing we know, but with these modifications," and that works up to a point. But eventually, if the new thing is sufficiently different, our analogies break down, our categories fail, and we're forced to either expand our framework or admit that we don't understand. That's uncomfortable. It's cognitively demanding. It challenges our identity as people who understand how things work. 3i Atlas is giving the astronomical community that experience right now. Every attempt to fit it into existing categories, comet, asteroid, hybrid, fragment, has failed or required so many qualifications that the category becomes meaningless. And so astronomers are being forced to sit with uncertainty, to admit ignorance, to accept that their decades of training and experience may not be sufficient to immediately understand this visitor from beyond. There's a lesson in that for all of us. In our personal lives, in our relationships, in our engagement with ideas and cultures different from our own, we constantly encounter things that don't fit our existing frameworks. And we have a choice. We can force them into ill-fitting categories, insisting that they must be variations of things we already know. Or we can sit with the discomfort of not understanding, remaining open to the possibility that we're encountering something genuinely new that requires us to expand our worldview. 3i Atlas, in its stubborn refusal to be easily categorized, is teaching astronomers humility. And that's a lesson worth learning, whether you're studying the cosmos or just trying to navigate the complexities of human existence. Let me tell you about a conversation that happened in February 2025 that perfectly encapsulates the current state of confusion and excitement around 3i Atlas. At the annual Division for Planetary Sciences meeting, held virtually this year, there was a special session dedicated entirely to 3i Atlas. Dozens of research teams presented their latest findings, and what happened was remarkable. Almost every presentation contradicted the previous one in some fundamental way. One team from the European Southern Observatory presented spectroscopic evidence that 3i Atlas contains significant amounts of water ice, consistent with it being a comet. The next presentation, from a group at MIT, showed thermal infrared data suggesting the object is far too warm in certain areas to have substantial water ice on the surface. Then a team from Kyoto University presented rotation light curve beta, indicating the object must be highly elongated, like Oumuamua. But this was immediately challenged by researchers from the University of Hawaii, who argued that the brightness variations could equally be explained by surface features on a more spherical object. Dr. Henry Hsieh, a planetary scientist who studies comets and asteroids, was moderating the session, and at one point he just laughed and said, "Well, we've now heard 6 different explanations for what 3I Atlas is, and I think each one has made a compelling case. The problem is they can't all be right, but I'm not sure any of them are wrong either." That comment really stuck with me because it captures the fundamental weirdness of the situation. It's not that some researchers are doing bad science and others are doing good science. Everyone is using rigorous methods, quality data, and sound reasoning, but they're arriving at incompatible conclusions. This suggests that the problem isn't with the science, it's with the underlying assumptions that everyone is making. Here's an analogy. Imagine you're a detective investigating a crime scene, and you find a footprint. One forensic expert analyzes the footprint and concludes it was made by a size 10 boot. Another expert analyzes the same footprint and concludes it was made by a size 12 shoe. A third expert determines it was made by a barefoot. All 3 are using valid forensic techniques and are highly experienced. How can they all be right? They can't. But maybe they're all wrong, because they're all assuming it's a human footprint, when actually it's from some animal they've never encountered before. The shape sort of matches human feet, so that's everyone's starting assumption. But the details never quite fit, because the fundamental assumption is incorrect. That might be what's happening with 3I Atlas. Everyone is assuming it fits into categories derived from solar system, objects, comet, asteroid, or some hybrid, because those are the categories we have. But what if 3I Atlas represents a category we've never encountered? What if interstellar objects that have been drifting for millions of years are fundamentally different in ways we haven't conceptualized yet? Dr. Małgorzata Kolakowska from the Space Research Center in Poland has been advocating for what she calls a phenomenological approach to 3I Atlas. Instead of trying to immediately fit it into existing categories, she argues we should simply catalog its properties without interpretation, building up a detailed description of what the object does, and only later try to develop theories to explain those behaviors. It's a more patient observational approach, and it's actually how much of astronomy was done before we had sophisticated theories. Astronomers would carefully document what they saw and only gradually develop explanations. The problem is that this approach is hard for modern scientists to accept because we're trained to form hypotheses and test them. We want explanations, not just descriptions. But Kolakowska has a point. Maybe we're trying to explain something we haven't finished observing yet. Maybe we need to just watch, document, and accumulate data, resisting the urge to interpret prematurely. This connects to something profound about how knowledge advances. Thomas Kuhn, in his famous book, The Structure of Scientific Revolutions, argued that science doesn't progress smoothly through steady accumulation of facts. Instead, it goes through revolutionary periods where existing frameworks are overthrown and replaced with new ones. These revolutions are triggered by anomalies, observations that don't fit existing theories. Oumuamua was an anomaly, but it passed through too quickly for us to gather enough data to really challenge our theories. 2I Borisov behaved normally and actually reinforced existing theories. Now 3I Atlas is emerging as a major anomaly, one that we're able to study in much more detail. The question is whether this anomaly is significant enough to trigger a revolution in how we think about interstellar objects, or whether it will eventually be accommodated within existing frameworks with some modifications. Based on the current trajectory of the research, I think we're headed for something genuinely revolutionary. Too many independent lines of evidence are pointing toward something weird. Too many researchers are independently reaching the conclusion that 3I Atlas doesn't fit existing models. The anomaly is too robust, too multifaceted, to be easily dismissed or explained away. But here's what's fascinating. Even if a revolution is coming, we can't predict what the new framework will look like. Revolutionary ideas in science are, by definition, things that people haven't thought of yet. When Einstein developed general relativity, overturning Newton's theory of gravity, the key insights curved spacetime. The equivalence of gravity and acceleration weren't things that could have been extrapolated from Newtonian physics. They were genuinely new conceptual frameworks. If 3I Atlas is going to force a revolution in our understanding of interstellar objects, that revolution will involve concepts and ideas that aren't currently on the table. Some young researcher somewhere might be developing the insight that will eventually explain everything. But right now, it's just a hunch, a half-formed idea, something they're not even sure is worth pursuing. That's how revolutions start, with someone willing to think outside the existing boxes. And here's the exciting part. That researcher could be someone who's currently watching this video. If you're a student, if you're interested in astronomy, if you're the kind of person who thinks deeply about puzzles and mysteries, you could be the one who figures this out. Scientific revolutions aren't always driven by senior, established researchers. Often they come from people early in their careers who haven't yet been fully indoctrinated into existing ways of thinking, who can see possibilities that more experienced researchers have been trained to dismiss. So if you're sitting there thinking about 3I Atlas and wondering what could explain all these contradictory observations, don't dismiss your ideas as naive or uninformed. Write them down, develop them, share them with others. Because the next breakthrough might come from someone asking a question that everyone else assumed was too simple or too strange to pursue. Now, let me tell you about one specific research direction that I think is particularly promising, even though it's currently considered highly speculative by most astronomers. It has to do with something called nuclear spin isomers and how they might behave in the extreme cold of interstellar space. Most people don't think about it, but many molecules can exist in different forms called isomers, which have the same atoms but arranged differently. Nuclear spin isomers are even more subtle. They have the same arrangement of atoms, but the individual atomic nuclei are spinning in different orientations. In normal conditions, these different spin states interconvert rapidly, and we don't notice any difference between them. But at temperatures near absolute zero, like in interstellar space, nuclear spin isomers can become frozen. They stop interconverting, and different isomers can persist for extremely long times. Some isomers have different chemical properties than others. For example, orthohydrogen and parahydrogen are spin isomers of H, and they have different heat capacities and slightly different reaction rates. Now, here's the wild idea. What if 3I Atlas is composed of materials where the normal balance of nuclear spin isomers has been disrupted by millions of years in interstellar space? What if it contains high concentrations of spin isomers that are unstable at warmer temperatures? As the object approaches the sun and warms up, these exotic isomers might start converting to more stable forms, releasing energy in the process, creating outgassing patterns that don't match normal sublimation. This theory was proposed by Dr. Darrell Seligman and his collaborator, Dr. Gregory Laughlin at Yale University, in a preprint paper that's currently circulating, but hasn't been peer-reviewed yet. Most astronomers are skeptical because there's no direct evidence for this hypothesis. We can't measure nuclear spin states from Earth-based observations. But the beauty of the hypothesis is that it could potentially explain multiple mysteries at once. The weird thermal properties, the unusual outgassing patterns, the confusing spectroscopic signatures. The problem is that this theory is nearly impossible to test without a spacecraft mission. You'd need to collect actual material from 3I Atlas and bring it back to a lab where you could analyze the nuclear spin states of the molecules. Given that we can't launch such a mission in time to catch 3I Atlas, this theory might remain forever speculative, at least for this particular object. But it opens up a broader question. Are there aspects of interstellar chemistry that we simply can't study through remote observation? Are there phenomena that only occur under the unique conditions of interstellar space that we can't replicate in laboratories on Earth? If so, then our understanding of interstellar objects will always be fundamentally limited until we develop the capability to send spacecraft to collect samples and bring them back. This is one reason why there's growing interest in what's called interstellar object sample return missions. The concept is simple but technologically challenging. Detect an interstellar object early, launch a fast spacecraft to intercept it, collect samples from its surface or coma, and return those samples to Earth for detailed laboratory analysis. The European Space Agency and NASA have both conducted preliminary studies of such missions, and while they're currently beyond our technological capabilities, they might be possible within the next few decades. Imagine what we could learn from even a few grams of material from an interstellar object. We could determine its exact composition, its isotopic ratios, its molecular structure, its age. We could search for organic molecules or even biosignatures. We could test theories about interstellar chemistry that are currently pure speculation. A single sample return mission could answer questions that centuries of remote observation can't. But until that happens, and it won't happen in time for 3I Atlas, we're stuck with the tools we have, trying to solve a mystery that might be fundamentally insoluble through remote observation alone. It's frustrating, but it's also a reminder of why space exploration matters. It's not just about taking pretty pictures or satisfying curiosity. It's about accessing information that we literally cannot obtain any other way. Now we need to talk about something that's been lurking in the background of this entire story, but that I haven't addressed directly yet. The possibility, however remote, that 3I Atlas isn't entirely natural. I know what you're thinking here comes the alien spacecraft theory, and I want to be very clear. There is zero evidence that 3I Atlas is artificial. But the reason this topic keeps coming up in discussions about interstellar objects is actually quite interesting and tells us something important about the scientific process. When Oumuamua was discovered and showed its strange acceleration without a visible coma, Dr. Avi Loeb proposed that it might be an alien light sail, a thin reflective sheet designed to catch starlight for propulsion. This idea was widely covered in the media and was deeply controversial in the astronomical community. Most astronomers argued that exotic natural explanations, while speculative, were still more plausible than invoking alien technology. The debate over Oumuamua taught us something important. Astronomers don't have a good framework for recognizing artificial objects if we encounter them in space. All of our methods for classifying celestial objects assume they're natural. We look at spectra and try to determine what minerals or ices are present. We analyze orbits and try to understand what gravitational forces are acting. We measure brightness and try to infer shape and rotation. All of these techniques work great for natural objects, rocks, ice balls, dust clouds. But what if we encountered something that wasn't natural? Would we recognize it? Or would we just keep trying to fit it into natural categories, adding more and more ad hoc assumptions to make it work, never quite realizing that we're looking at something designed rather than something formed by physical processes? This is actually a serious question in the field of SETI, the search for extraterrestrial intelligence. Researchers worry about the alien under the streetlight problem. We search for signals that we would recognize as artificial. But what if alien technology is so different from ours that we wouldn't recognize it even if we saw it? We might be surrounded by evidence of extraterrestrial technology and not realize it because we're looking for the wrong signatures. Now, to be absolutely clear, 3I Atlas shows no signs of being artificial. It's not transmitting radio signals. It's not following a trajectory that suggests intelligent guidance. It doesn't have the optical properties of manufactured materials. Every weird thing about it can potentially be explained by exotic natural processes, even if we haven't figured out exactly which natural processes yet. But, and this is important, the mere fact that 3I Atlas is so confusing that it resists being classified into natural categories has led some researchers to at least consider whether we might be looking at something we don't have a natural explanation for. Not because they think it's likely to be artificial, but because scientific rigor requires considering all possibilities, even ones that seem unlikely. Dr. Jason Wright at Penn State, who studies both exoplanets and SETI, has written about this issue. He argues that we need to develop better criteria for distinguishing natural from artificial objects, because as our technology improves and we start detecting smaller and smaller objects in interstellar space, we're eventually going to encounter things that are genuinely ambiguous. And if we don't have a good framework for evaluating such objects, we might either miss something important or waste resources chasing false positives. The criteria he proposes are interesting. An artificial object should show evidence of design patterns that are unlikely to occur naturally, materials or structures that require manufacturing processes, behavior that suggests purpose or function rather than just physical laws. By these criteria, 3I Atlas doesn't qualify. Yes, it's weird, but weird isn't the same as designed. Natural processes can produce weird results, especially when they operate under conditions we've never studied before. However, Wright also points out that our intuition about what's unlikely to occur naturally is based entirely on our experience with our own solar system. If we encounter something from a radically different environment, something shaped by billions of years of processes we've never observed, our intuitions might fail us. We might call it impossible, when really it's just impossible under the conditions we're familiar with. This connects back to the earlier point about the limits of knowledge. We can only recognize artificial objects by contrast with natural ones. If something is sufficiently unlike anything natural we've encountered, and we can't explain it with known natural processes, we face an epistemological crisis. Is it artificial, or is it natural, but formed under conditions so different from anything in our experience that we can't recognize it as natural? 3I Atlas isn't pushing us into that crisis, not yet anyway, but it's getting close. A few more interstellar objects like this, each one breaking our theories in new and inexplicable ways, and we might find ourselves in a situation where we genuinely can't tell what we're looking at. And here's the philosophical bomb I want to drop. Maybe that's okay. Maybe the universe is under no obligation to be comprehensible to us. Maybe there are objects and phenomena out there that we will never fully understand, not because we're not smart enough, but because we don't have access to the necessary information, or because our conceptual frameworks are fundamentally inadequate. This is a humbling thought, but it's also liberating. It means the universe is genuinely mysterious, genuinely unknowable in its entirety. And that means there's always something more to discover, always another surprise waiting. We'll never reach a point where we've figured everything out and there's nothing left to learn. 3I Atlas is reminding us of this. Even with all our technology, all our knowledge, all our sophisticated theories, we can't figure out what this one object is. And that's not a failure. It's a revelation. It's the universe telling us, you're not as clever as you think you are. There's more going on here than you understand. Stay humble. Stay curious. Keep looking. In a weird way, I find that message comforting. I don't want to live in a universe where everything is already figured out, where there are no real mysteries left, where every question has a tidy answer in a textbook. I want to live in a universe that can still surprise us, still challenge us, still show us things we've never imagined. And right now, that's exactly the universe 3I Atlas is revealing. Let me take you into the future now, because one of the most exciting aspects of the 3I Atlas story is what it means for the next decade of astronomy and space exploration. The lessons we're learning from this object are already influencing how we design future telescopes, plan future missions, and think about our strategy for studying interstellar visitors. First, there's the Vera C. Rubin Observatory, previously known as the Large Synoptic Survey Telescope, which is scheduled to begin operations in late 2025. This facility in Chile will revolutionize our ability to detect interstellar objects. It will survey the entire visible sky every few nights, automatically flagging anything that moves. Current estimates suggest that once Rubin is operational, we'll detect somewhere between 1 and 10 interstellar objects per year, compared to the roughly 1 per decade we're detecting now. Think about what that means. We'll go from studying interstellar objects as rare, once-in-a-lifetime events to having a regular stream of them to analyze. We'll be able to compare them, categorize them, look for patterns. We'll discover whether 3I Atlas is truly anomalous, or whether it's actually typical of a class of interstellar objects that we just haven't seen enough examples of yet. Dr. Mario Jurek at the University of Washington, who's involved with the Rubin Observatory, told me that he expects the first year of operations to be absolute chaos as the astronomical community tries to follow up on dozens of potential interstellar objects with limited telescope resources. But he also expects that within 5 years, we'll have a much better understanding of the population of interstellar objects, their sizes, compositions, trajectories, and diversity. And here's what's really exciting. Some of those objects will inevitably be even weirder than 3I Atlas. We're going to discover things that break our theories in new and unprecedented ways. Each one will be a puzzle, a mystery, a chance to learn something fundamental about the universe. The next decade is going to be a golden age for this field. But detection is only the first step. We also need better tools for characterizing these objects once we find them. That's where the next generation of extremely large telescopes comes in. The giant Magellan telescope in Chile, the 30-meter telescope hopefully in Hawaii, and the European Extremely Large Telescope, also in Chile, will all have the light-gathering power and resolution to study interstellar objects in unprecedented detail. With these telescopes, we'll be able to obtain high-quality spectra showing detailed chemical compositions. We'll be able to resolve surface features, track rotation precisely, detect faint comas and tails. The kinds of observations that currently require the Hubble Space Telescope and weeks of observation time will become routine. We'll be able to study interstellar objects not as fuzzy dots that barely stand out from background stars, but as real objects with observable properties. And perhaps most importantly, we're starting to think seriously about sending spacecraft to these objects. The European Space Agency is developing a concept called Comet Interceptor, which would involve launching a spacecraft to a stable gravitational point in space where it would wait for an interesting comet or interstellar object to be detected. Once a target is identified, the spacecraft would quickly maneuver to intercept it. This mission could launch as early as 2029 and would be capable of reaching a newly discovered long-period comet or potentially an interstellar object if we detect one with sufficient lead time. NASA is considering similar concepts. The idea is to have spacecraft already in space, ready to go, rather than trying to design, build, and launch a mission after an object has been detected, by which point it's usually too late. It's an expensive approach because you're maintaining a spacecraft in space, waiting for a target. But the scientific payoff could be enormous. Imagine if we had had Comet Interceptor in space when 3I Atlas was discovered. Instead of trying to puzzle out its properties from Earth-based observations, we could have sent a spacecraft to fly by it, taking close-up images, measuring its composition directly, sampling its coma, maybe even landing on it. We could have answered definitively what it's made of, how it's structured, why it behaves the way it does. That data would be worth more than decades of remote observations. But even without a dedicated mission to 3I Atlas, the object is teaching us how to prepare for future opportunities. Every observation we make, every technique we develop, Every lesson we learn about what works and what doesn't, all of it, is building institutional knowledge. That will pay off when the next interesting interstellar object comes through. And there's another development that could revolutionize this field: artificial intelligence and machine learning. Several research groups are now training AI systems to analyze astronomical data, looking for patterns that human researchers might miss. These systems can sift through millions of observations, flag anomalies, and even suggest hypotheses about what might explain unusual behavior. Dr. Federica Bianco at the University of Delaware has been developing machine learning algorithms specifically for studying transient astronomical phenomena, things that change over time, like supernova, variable stars, and yes, comets and interstellar objects. She believes that AI could help us make sense of confusing objects like three-eyed Atlas by finding subtle patterns in the data that aren't obvious to human observers. For example, an AI system might notice that certain types of brightness variations always occur at specific positions in the orbit, or that spectroscopic features correlate with thermal properties in non-obvious ways. These kinds of patterns could provide clues about what physical processes are occurring, even if we don't immediately understand the underlying mechanism. The combination of better detection capabilities, more powerful telescopes, spacecraft missions, and AI analysis tools means that the field of interstellar object studies is poised for explosive growth over the next decade. What's currently a niche specialty involving a few dozen researchers could become a major branch of astronomy involving hundreds of researchers and billion-dollar missions. And all of this is being driven by objects like Three-Eye Atlas that refuse to fit into our neat categories and force us to think harder, observe better, and develop new tools and techniques. Now I want to bring this back to you personally, because I think there's a profound lesson in the Three-Eye Atlas story that applies far beyond astronomy. It's about how we deal with uncertainty, how we navigate a world that's more complex and ambiguous than we'd like it to be, and how we find meaning and purpose in the face of questions that might not have answers. When you first started watching this video, Three-Eye Atlas was just a name, maybe not even that, just a vague concept of some mysterious object in space. But now, after spending this time with me learning about it, the object means something to you. You understand the mystery. You feel the frustration of scientists trying to make sense of contradictory data. You appreciate the stakes of studying something that will soon be gone forever. This is how we create meaning, by investing attention, by developing understanding, by caring about things beyond our immediate personal experience. Three-Eye Atlas doesn't affect your daily life. It's not going to crash into Earth, or change the weather, or alter the stock market. In practical terms, it's utterly irrelevant to you. And yet, I'd bet that right now you care about it. You want to know what it is. You're curious about what future observations will reveal. You've made an emotional investment in this mystery. That's a profound human capacity, our ability to care about things simply because they're interesting, because they're mysterious, because they expand our understanding of what's possible. No other species we know of does this. Animals care about things that affect their survival and reproduction. But humans? We care about distant objects in space, about ancient history, about abstract mathematics, about fictional characters in novels. We seek meaning and connection beyond the immediate and practical. And here's what I think is beautiful about that. By caring about Three-Eye Atlas, you're participating in something larger than yourself. You're part of a global community of people scientists, educators, enthusiasts, curious individuals who are all collectively trying to understand this one mysterious object. Your attention matters. Your curiosity matters. Because collective attention is what drives science forward. When lots of people are interested in something, funding agencies pay attention. Telescope time gets allocated. Young students get excited and decide to become astronomers. New technologies get developed. The entire enterprise of understanding moves forward, not just because of brilliant individual scientists, but because of a whole ecosystem of people who care enough to pay attention. So by watching this video, by learning about 3I Atlas, by maybe sharing this story with others, or following future developments, you're actually contributing to something real and important. You're part of the story. And this connects to a broader point about how we navigate uncertainty in our lives. The scientists studying 3I Atlas don't know what it is. They're dealing with incomplete information, conflicting data, and theories that don't quite work. And yet, they keep going. They keep observing, analyzing, discussing, and theorizing, even though they might never fully understand this object before it disappears. That's a model for how to live wisely. In life, we're constantly faced with situations where we don't have complete information, where different sources tell us different things, or our mental models don't quite fit reality. We can respond to this in several ways. We can become paralyzed by uncertainty, unable to act because we don't know enough. We can become dogmatic, insisting that our current understanding is correct and refusing to update it when new information arrives. Or we can be like good scientists holding our current best theories lightly, remaining open to new information, accepting that our understanding is always provisional and incomplete, but still making the best decisions we can with what we know. The scientists studying 3I Atlas model this third approach beautifully. They're not paralyzed. They continue making observations and running analyses. They're not dogmatic. They're willing to revise their theories when new data arrives. They live in the uncertainty, accepting it as a fundamental feature of the endeavor, not a temporary inconvenience to be eliminated. And they find meaning and purpose in the search itself, not just in the answers. The journey of trying to understand 3I Atlas, even if they never fully succeed, is valuable. The observations they make, the techniques they develop, the collaborations they form, the conversations they have, all of this as value independent of whether they definitively solve the mystery. That's a powerful life lesson. We often think that meaning comes from achieving our goals, from finding answers, from solving problems. But actually, much of life's meaning comes from the pursuit itself, from engaging fully with challenges, from learning and growing, from connecting with others in shared endeavors, from pushing the boundaries of what we understand. 3I Atlas is teaching us this lesson at a cosmic scale. It's a mystery that may never be fully solved, at least not before the object disappears from view. But the effort to understand it, the observations, the debates, the theories, the excitement, the frustration, all of that is meaningful and valuable in itself. And here's the final mind-blowing connection I want to make. Your life is like 3I Atlas in a weird way. You're a unique object, shaped by a complex history you only partially understand, following a trajectory through time and space, observed by others who try to understand you, but probably never fully succeed. You don't fit neatly into categories. You're surprising, sometimes even to yourself. You contain contradictions that don't resolve easily. And just like 3I Atlas is valuable and fascinating precisely because it's mysterious and doesn't fit our expectations, you are valuable and fascinating for the same reasons. The things about you that don't fit societal expectations, that confuse people, that resist easy categorization, those aren't bugs, they're features. They're what make you interesting, what make you worth knowing. So when you feel like you don't fit in, when you feel like people don't understand you, when you feel like you're too complex or contradictory to be easily explained, remember 3I Atlas. Remember that the most interesting and valuable things in the universe are the ones that challenge our understanding, that force us to expand our categories, that remind us that reality is richer and stranger than our theories about it. Be like 3I Atlas. Be mysterious. Be unexpected. Break people's theories about who you should be. And trust that the right people, like good scientists, will find that fascinating rather than frustrating, and will want to understand you more deeply rather than giving up and moving on to something simpler. We're coming to the end of our journey together, but I want to leave you with the absolute latest developments and what to watch for in the coming months. Because remember, this story isn't over. It's still unfolding in real time, and you now have the knowledge to follow it as it develops. As of when I'm recording this, 3-1 Atlas is currently about 380 million kilometers from the Sun, moving inward on its hyperbolic trajectory. It's getting brighter as it approaches, which means our observations are actually improving week by week. The best observations are likely to come in late spring and early summer of 2025, when the object will be closest to both the Sun and Earth, maximizing both its intrinsic brightness and our ability to see detail. Several major observation campaigns are planned. The James Webb Space Telescope has dedicated time scheduled for mid-April 2025 to obtain the highest quality spectra yet. These observations could potentially resolve the chemical composition ambiguities that have plagued earlier studies. The Very Large Telescope in Chile is conducting near-weekly observations to track any changes in activity, and multiple radio telescopes are monitoring for any emissions that might tell us about gas production rates. There's particular excitement about observations planned for when 3I Atlas reaches perihelion, its closest approach to the Sun, which should occur around June 2025. This is when any volatile ices should be sublimating most vigorously, producing the strongest coma, and potentially revealing the object's true composition. If the weird behavior continues or intensifies at perihelion, it will definitively rule out many current theories. If, on the other hand, the object suddenly starts behaving like a normal comet, it might suggest that whatever exotic processes were occurring at larger distances stop working once the object gets warm enough. Here's what you should watch for in news and social media about 3I Atlas. First, any announcements about the object fragmenting further. If the pieces we've already identified continue separating, or if new fragments appear, it could tell us about the object's internal structure and what's causing the strange behavior. Second, any reports of major outbursts. A sudden brightening would indicate some kind of structural change or exposure of fresh material, and could provide crucial clues about what's happening beneath the surface. Third, any announcements of successful spectroscopic identification of specific molecules. If researchers can definitively identify what the object is made of, that would be huge. Look for phrases like detection of X molecule confirmed, or spectroscopic signature consistent with Y. Fourth, any proposals for future missions. If 3I Atlas continues to be mysterious enough, it might motivate funding agencies to approve new missions designed to intercept future interstellar objects. Watch for announcements from NASA, ESA, or other space agencies about mission concepts or feasibility studies. And finally, and this is important, watch for the scientific consensus to shift. Right now, there's no consensus about what 3I Atlas is. But at some point, either a compelling explanation will emerge that most astronomers accept, or the community will collectively admit that we can't explain it with current knowledge. Either outcome would be significant and would shape how we approach future interstellar objects. You can follow developments through several sources. NASA's website has a section on interstellar objects where they post updates. The arxiv.org preprint server is where astronomers post their research papers before formal peer review, so you can see cutting-edge results months before they appear in journals. And social media, particularly Twitter X, where many astronomers share observations and discuss results in real time. I'll be posting updates as well, so make sure you're subscribed and have notifications turned on. But beyond just following the news, I want to encourage you to think about what 3I Atlas represents. It's a reminder that we live in a universe that's still full of surprises, that our knowledge is always provisional, that the next observation might change everything we think we know. It's a reminder that humanity's quest to understand the cosmos is ongoing, that we're not nearly as advanced as we sometimes imagine, that there are profound mysteries still waiting just beyond our current ability to observe and understand. It's a reminder that science isn't a collection of facts in a textbook. It's a living, breathing process of discovery, full of false starts and dead ends and confusing contradictions, but gradually, fitfully, moving toward deeper understanding. And most importantly, it's a reminder that you live in a time when these discoveries are happening, when the frontier of knowledge is being actively pushed, when questions that have puzzled humanity for all of history are finally starting to get answers, and when new, even deeper questions are being revealed. This is an extraordinary time to be alive. We're detecting gravitational waves from colliding black holes billions of light years away. We're finding thousands of planets around other stars. We're unraveling the mysteries of dark matter and dark energy. We're detecting interstellar visitors passing through our solar system. And you get to witness it all? Don't take that for granted. Don't let it become background noise. Pay attention. Be curious. Ask questions. Wonder about things. Because this moment in history, when humanity is actively exploring and discovering and expanding the boundaries of knowledge, this is special. This is worth caring about. 3I Atlas is just one small object, a chunk of ice and rock, maybe a few kilometers across, falling through the solar system on a trajectory that will carry it back into the darkness of interstellar space within a year or two. In the grand scheme of the universe, it's utterly insignificant. But to us, to the scientists studying it, to you watching this video, to humanity collectively trying to understand what this visitor means, it's anything but insignificant. It's a messenger from beyond, a puzzle to be solved, a challenge to our understanding, and a reminder of how much we have yet to learn. So here's my final challenge to you. Don't just passively watch this story unfold. Engage with it. Think about it. Talk about it with friends and family. Follow the developments. And when 3I Atlas finally fades from view, disappearing back into the cosmic ocean from which it came, remember what it taught us. Remember that the universe is stranger than we imagine. Remember that our theories are always incomplete. Remember that mystery and wonder are not bugs to be eliminated, but features to be celebrated. Remember that every answer we find opens up new questions. And remember that you're part of this part of humanity's long journey from ignorance to understanding, from fear to knowledge, from isolation to connection with the wider cosmos. That's the real story of 3I Atlas, not just what it is, but what it means for us, for how we see ourselves and our place in the universe. It's a story about humility and wonder, about the limits of knowledge and the infinite capacity for curiosity. And it's a story that's still being written by scientists around the world, by the object itself as it continues its journey, and by you as you think about what you've learned and what it means to you. Thank you for taking this journey with me. Thank you for caring about a mysterious object billions of kilometers away that has no direct impact on your life, but that represents something profound about the human spirit, our endless curiosity, our drive to understand, our capacity for wonder.